Welcome to Going Lower. This is the first video in a planned series in which we try to get closer to the silicon from the perspective of high-level languages like C#, Kotlin, JavaScript, and Python. For most programmers, the emphasis is rightfully on going higher by adding more levels of abstraction in library or language. But I feel that going lower is also important and often overlooked. There is a real sense of satisfaction in trying to understand all the layers below C#. And when it comes to high-performance computing, this understanding becomes critical. In future episodes, I plan to explore this in much more detail. Today, however, I wanted to give a taste and introduction by exploring a very simple loop. In this case, on the left, we have a for loop in C#. At compile time, the source is transformed into intermediate language, IL. At runtime, it is just-in-time compiled or jittered to assembly. Assembly language has a near one-to-one correspondence with binary code, and it is this that the CPU rarely executes. Let's start by introducing the visual debugger. On the left is our C# code. Next to that is the binary code in RAM. This binary code is executed by the arithmetic logic unit, ALU. It operates a fetch, decode, and execute cycle. For clarity, the execute cycle is split into read and write. Each logic unit has its own memory in the form of registers. To make better sense of the assembly code, we need to have a look at register names. The easiest way to understand the register names is from its history. The x86 instruction set is around 30 years old. It started life as the simple 16-bit 8086 processor, hence the family name. Later it doubled to 32-bit, finally doubling again to 64-bit. The register names reflect this progression. Take for example the A register. It was originally called AX in its 16-bit form, then added an E to become 32-bit, lastly adding an R to become 64-bit. The same holds for the other registers. We are finally ready to watch some code running. Our first step is to initialize the sum variable to 0. On the right, the instruction pointer holds a location in RAM for the next instruction to execute. Fetch decodes this from RAM and sends it to execute. Here, 33C0 means XOR the A register with itself. For convenience, we've marked the A register as holding the sum variable, and the fact that it is in its 32-bit, not 64-bit variant. XOR any variable with itself or any register with itself is a fancy way of setting that variable to 0. They do it because it is faster. Here we can see the read, which doesn't matter much as we're setting to 0, and the write, where we have the result, is 0. Now our sum value is initialized. Similarly, we now set the x variable to 0 with the same mechanics. Here, the x variable is mapped to the source index. The choice of which registers are used for which variables is the subject of another video. I'll look at it in the future. Next, we have a guard. If count were to be 0, there would be nothing to do and we want to exit early. Comparisons and tests and assembly are done in two parts. First, a logic operation that doesn't change state, but rather sets flags. Then, based on those flags, a conditional jump. Here, we're testing if the DI register is 0. So we do the test and you can see the flags changing. Next, a conditional jump. We already know that 5 is greater than 0, so we don't take the purple line. we are now in the inner loop where we accumulate x to the sum variable. This time around it's a little boring as both are already 0. 0 plus 0 is 0. Now we increment the x variable, so add 1 to that, straightforward. You can see the input is 0, the output is 1. Now for the exit conditions. The exit condition is an easier comparison to jump into. We want to understand whether the x value is less than count, so we compare the two inputs, the source index which holds x, which is 1, and the destination index, which is the count, which is 5. That will then set flags. So we can see based on that, the carry flag, parity flag, adjust flag, and sign flag have been set. The second part is a conditional jump based on those flags. In this case, we care if the sign flag is not equal to the overflow flag. And this is the case. The sign flag here is set, and the overflow flag here is not set. So we would jump taking the purple line. Back in the inner loop. This time round we accumulate 1 to the existing total, and we increment x. Now 2. I'm going to jump through the remaining 2, 3, 4, and 5 inner loops. 3, 4, and finally 5. Now our comparison state should be different. When we do the compare, we see the parity flag and 0 flag are set. Now SF is equal to OF, and we don't take the jump. Here we exit the loop, and we've got to the end of our for loop with our accumulated sum being 10. We're now at the end of our loop, where the accumulated sum is 10, which is returned out. That wraps up our introduction. In further videos, we will get into much more interesting cases. If you want more details, have a look at the Intel Developer Introduction. Unlike the full manual, which is thousands of pages, this PDF is short and accessible. The x86 primer is a good way of getting into assembly language rather than decompiling from higher level languages. If you want to look up an individual opcode, this wiki is a great resource. Please leave a comment below if you have any suggestions on how to improve this video, or questions or content you would like me to cover in further ones. Once again, thank you so much for watching.